Good morning. Today we're going to talk about section 5.7 entitled Difference of Squares. And this is one of our special product type patterns, and we're going to exploit this pattern to hopefully make it a bit easier to factor some somewhat complicated expressions. Well, we know that when we multiply conjugate binomials, by that I mean binomials where the sign in between is different. They're not opposites, but the sign in between is opposite. When we multiply expressions of this type, well, if I multiply the first product, I get a squared. The outer product, I'll call negative a times b. The inner product is b times a, which I can equivalently call plus a times b. And the last product, excuse me, is negative b squared. Of course, in this special pattern, when multiplying conjugate binomials, the outer and inner products cancel out, and I'm left with a difference of squares. So I'm going to exploit this pattern here and claim if I can recognize an expression as a difference of two squares or equivalent to the difference of two squares, I can instantly factor it, if I recognize that pattern, into the sum of the two bases times the difference between the two bases, a plus b times a minus b. Alright, so let's circle this. I'll call this my difference of squares factoring pattern and jump right in and do a few examples of this type. Example. Let's say I factor x squared minus 9. Alright, maybe this is a little too simple for us, but I think we can easily claim this is equivalent to x squared minus 3 squared. 9 is certainly a perfect square. And of course, according to our pattern, this will break down factor as x plus 3 times x minus 3. Let's do something a little tougher. 81 times p squared minus 25. Well, hopefully we recognize 81 as a perfect square. P squared is of course a square, and 25 is also a perfect square. I can claim this is going to be the square of 9p minus the square of 5. Now, I don't really have to be so formal in rewriting it explicitly as a difference of two squares. Hopefully we can recognize the pattern here and instantly write down the answer. If we know the pattern, it's going to be 9p plus 5 times 9p minus 5. Okay? Alright, so there's our factored answer for that example. Now, another one of this type. 64 a to the fourth minus 25 b squared. Now I know what you're thinking. You're thinking that this is supposed to be difference of squares, and I see a fourth power there. Well, hopefully we can agree that a fourth power can be written as a power of 2, can it not? I can rewrite the first term in that binomial as 81 a squared squared, can I not? And that second term I can rewrite as 5 times b squared, can we not? So we can easily see now this is really the difference of two squares, and really then the sum of the two bases times the difference, 8a squared, times the difference between the two bases, 8a squared plus 5b times 8a squared minus 5b. Again, you can always check your answer in a factoring problem. Hopefully you can convince yourself when we multiply these two binomials, you do end up with what you started with. Notice the first product is 64 a to the fourth, just like we saw in the original. The outer and inner products will cancel out. They'll be equal in magnitude but opposite in sign. And the last product will be minus 25b squared. So it does indeed check. I don't insist that you check every problem, every answer, but if maybe in a tougher problem, if you're a little bit queasy about it, it would behoove you to check your answer. Alright, let's go on. Factor. And just like you'd see it on a exam, a to the fourth minus 81. Again, factor means to rewrite equivalently as a product of factors, and you have to break it down as far as you can. Well, of course, any fourth power, as we saw in the last example, can be considered a second power. I can break this down as a squared plus 9 times a squared minus 9. Can we not? Alright, and hopefully you can see we can break this down further. Factor again. A squared minus 9 is also a difference of two squares. Now, don't forget to carry any other factors down to your final answer. A squared minus 9 breaks down as a plus 3 times a minus 3. And I want to highlight something here. Notice, one of my factors in the final chain is a sum of squares. Now, a sum of squares never will factor, right? Does not factor. It's that negative sign in the difference of two squares that allows for that opposite signs of the inner and outer product, or the cancellation of that inner and outer product. So, sum of squares does not factor. It's a prime factor, which must be included in your final answer. Alright, so I'm going to box this as my final answer. Of course, you can rearrange the order of these factors and get an equivalent answer, right? Because multiplications, of course, are commutative and associative. Okay? Important to remember, sum of squares does not factor. Try another one. 2 x to the fourth power y minus 32y. And again, you're thinking, this doesn't look like difference of squares. Well, I think if we play around with this expression a little bit first, we may see something unfold. Again, in any factoring problem, we'll look for the GCF first. And I think we can see a GCF here of 2y. Can we not? We factor out a 2y. I'll get a resulting expression, x to the fourth minus 16. Alright, once I factor out that GCF, I clearly see a difference of squares pattern emerging. Don't forget to carry that GCF down to your final answer. X to the fourth minus 16 as a difference of squares. That'll factor as x squared plus 4 times x squared minus 4. Alright, so we factored twice in this problem already, and I think we can still factor again. This x squared minus 4 is also a difference of squares. 2y is a prime factor that'll carry down to my final answer. X squared plus 4, remember, sum of squares does not factor, but you must carry that prime factor to your final answer. And finally, x squared minus 4 is going to be x plus 2 times x minus 2. Alright, so I factored 3 times in this one problem to arrive at a most completely broken down or factored answer. I've rewritten the original product as kind of a long chain of prime factors. So this is my completely factored answer. And again, let me notice here, sum of squares does not factor. It's prime. Doesn't break down, but you must carry that prime factor and all prime factors down to your final answer. Okay. Try another one. X to the fourth minus y to the fourth. Again, I can view any even power as a second power of something. Alright, so I claim this factors as x squared plus y squared times x squared minus y squared according to my difference of squares pattern. Again, the sum of squares is prime, but you must carry it down as a element of your final answer. And of course, x squared minus y squared is a difference of squares. I can factor this as x plus y times x minus y. And again, you can rearrange the order of these factors in any way you like. And there's my final answer. Another 81 m to the fourth power minus 256 n to the fourth power. Now I get a little nervous. 256 got a lot of possibilities. At first I thought I could factor out a GCF, but 256 is not a multiple of 81. Well, what I can do is recognize, well, certainly m to the fourth is a second power of m squared. N to the fourth is a square. 81 is the square of 9. 256, it turns out, is the square of 16. Alright, so I can easily break this down as 9m squared plus 16n squared times 9m squared minus 16n squared. Alright, sum of squares does not factor, prime. Won't break down any further, but you need to carry it down to your final answer. 9m squared minus 16n squared is indeed a difference of squares, so this will break down as 3m plus 4n times 3m minus 4n. Final answer right here. You can check it if you want to multiply it backwards and multiply it, see what you end up to get what you started with, but I'm not going to insist. Okay? New layer. Example. Factor 288 b squared minus 2b to the sixth power. Well, so the highest degree exponent doesn't always have to be listed first in order left to right. Well, look for a GCF. Always look for a GCF first in any factoring problem. And what's the GCF here? Well, I think I see a factor of 2 that I can factor out, and I can factor out a b squared from this binomial. So 2b squared is going to be a GCF. What's left inside? Then 144 minus b to the fourth power, right? And of course, I recognize 144 is the square of 12, and b to the fourth is the square of b squared. Don't forget to include all your previously factored elements into your final answer. So I must carry the 2b squared down to my final answer. Alright, so 144 minus b to the fourth factors as 12 plus b squared times 12 minus b squared. And I claim that's a final answer. 12 plus b squared, of course, is prime. And 12 minus b squared, well, 12 is not a perfect square. So I claim this is also prime. So I've reduced my original expression into a list of multiplied prime factors. And there's my final answer. 2b squared times 12 plus b squared times 12 minus b squared. Alright, so that's not too tough once you practice these a few times, hopefully. I believe this next one's on your homework list. 81 c to the fourth d to the fourth minus 16 t to the fourth power. Well, again, I should look for a GCF first, but I don't see any meaningful GCF here. I'm not going to bother to factor out a 1 or a negative 1. Looking for something beyond that. Well, 81 is a square, c to the fourth, d to the fourth are squares. 16 is a square, and of course t to the fourth power can also be viewed as a square. I'm going to jump right to it. I'm going to call this 9c squared d squared plus 4t squared times 9c squared d squared minus 4t squared. Alright? And this factor is a sum. This is a t. Let me rewrite that. That's a t there. 4t squared. Alright. This first factor in the list is prime. It's a sum of squares, so carry it down to your final answer. But of course, I can factor again. 9, c squared, d squared, 4, and t squared are all squares. So I can break it down again is 3cd plus 2t times 3cd minus 2t. So applying my difference of squares pattern twice in the same problem, I get this completely factored answer. 2 more today. Factor 100a squared plus 9b squared. Alright, now a lot of people try to factor this, and probably the easiest way to deal with this one is to recognize this as a sum of 2 squares. And as we've said many times today, sum of squares is prime. It will not factor, so this is impossible to factor. Remember, if I ask you to factor, well, let's say, oops, hang on, 100a squared minus 9b squared, well, that's a different story. Remember, it's this negative sign here that allows for the cancellation of the outer and inner products. So I can easily factor this as 10a plus 3b times 10a minus 3b. Moral of the story, sum of squares is prime. And I believe this next one's the last one on your homework list. Pretty much represents the upper limit of difficulty here. Factor 5ab to the fourth minus 5 times a. Well, a lot of students might get thrown by this problem unless you look for a GCF first. Get that GCF out of there, and clearly I see 5a as a common factor in this binomial difference. If I factor out a 5a, I'm left with b to the fourth minus what? Well, if I factor out a 5a from that slot, I got to leave the invisible 1. And of course, b to the fourth minus 1, well, 1 to any power is 1, so I can view 1 as, of course, as a square. So I'll get 5a times b squared plus 1 times b squared minus 1. And again, don't be fooled. B squared plus 1 is a sum of squares, so this factor is prime. Of course, 5a can't be broken down any further. That's prime. So carry down all your prime factors to your final answer. And this b squared minus 1 is, of course, a difference of squares again. So I'll call this b plus 1 times b minus 1. So there's my final answer, completely factored answer. I've broken it down into really 1, 2, 3, 4, 5 factors if you count 5 as a separate factor. Or 1, 2, 3, 4. You could claim there's 4 prime factors in that original expression. Alright, so that ends it for today. We'll call it a day with 5.7 difference of squares.